Welcome back to ME 760, Engineering Analysis 1. So we are done with chapter number 9, the vector algebra. And now we will be moving to chapter number 10, matrices and linear vector spaces. So we will start with the definition of vector linear spaces. It's an abstraction, it's abstract mathematics, so maybe you will find the definition more abstract, but hopefully by the end of this lecture we will give a couple of examples, for example, to define what's the linear vector spaces. If not, it will be next lecture. So let's start. So this is chapter 10. Matrices and vector spaces. So we will define what we mean by a vector space. So how many of you heard about the concept of set? Do you know what a set is? So a set is just a collection of objects. And if you have, for example, let's say the alphabet. So the collection of alphabet, we will say that this is the set of alphabet. People, we will say this is the collection of people in the high school, or students in the high school. Integer, we can say that this is the collection of integer, and so on. And usually you can get subsets of the set, of the whole set. So a set is just a collection of the objects. The order is not important, so you can put 1, 2, 3, 4, 5, or 3, 4, 5, 1, or whatever. And repetition is also not important. 1, 1, 1, 2, 3, 4, 4, 5. It is 1, 2, 3, 4, 5. So this is just a nutshell, in a nutshell, the definition of sets. So if we have a set, a set of all vectors, let's assume that we have vectors A, vectors B, vectors C, and so on, is said to form a linear vector space V. So we have a vector space named V of vectors A, B, C, and so on, if certain conditions will be fulfilled. And by the way, we'll be talking just about vectors for right now, but we will extend our linear vector spaces to more general definition. So as I just stated, the set will be objects. So in this case, we are talking about a set of vectors. Maybe each one of those, instead of a vector, will be a 2 by 2 matrix. So it will be a vector space of 2 by 2 matrices. So maybe instead of a vector, it will be polynomial. So we will have an n-dimensional vector space of polynomials. So in this case, the component of the set will not be a vectors, but will be polynomials, and so on. So the abstraction will require that we will have the elements of the set will be any mathematical object, whether the mathematical object will be a vector, or it will be a function, or it will be a matrix, or whatever. So we are talking just right now for the objects of the set will be just normal vectors, and we'll expand the definition later on the definition of vector spaces for matrices or whatever mathematical object that we have. So first of all, the first condition, the set is closed. The set is closed under commutative and associative addition. What does mean a closed set? A closed set, and here a closed set under certain operation. What are the operation? Addition, commutative addition, and association. What does it mean? So let's assume that we define the set of all, let's say, set of all integers. 1, 2, 3, 4, 5, 6, 7, 8, 9, up to infinity. So if you do addition over those numbers, so you said 1 plus 2 is what? 3. 3 is in itself an element inside the set that contains all the integer. So in this case, the addition is commutative, 1 plus 2 is 2 plus 1, and is associative, 1 plus bracket over 3 and 4 is equal to 1 plus 3 bracket plus 4. So if we have this definition, we will say that the set is closed because any resultant or any results of the addition will be an element that exists inside the same set. This is why they call the set is closed under operation. In this case, the set is closed under commutative and associative addition. So if we add any of those vectors together under the commutative and associative manipulation, it will be another element inside the same set. This is why the set is closed. So here is the definition. If we have the vector A plus vector B, this will give us vector B plus vector A, and this is again the commutative addition, and this is A plus B. We add them together first, then we add vector C to them. It will be, so this is the association, it will be A plus vector B plus vector C. So if we have this two properties, the summation here, A plus B and B plus A, will be the same number, and it will belong to the same set of vectors, A, B, C, D. It will not give me a vector outside this set. And also the distribution or association property will give me a vector that's already exist in the same set. It's not outside the set. So this is the first property. The second one is the set is also closed under scalar multiplication. So set is closed under multiplication, scalar multiplication. And the operation, we have the distributive property and the associative property. So let's assume that lambda is a scalar quantity, and if we multiply lambda by A plus B, then you will distribute lambda over A and lambda over B, and this is the distributive property. So lambda A plus lambda B. So this is the distributive. Property. If you have two constants, lambda plus mu, scalar quantities, and you multiply this by A, again it will give you lambda A, same distribution, plus mu multiplied by A. And here's the association. So this is lambda multiplied by mu A. This will give you lambda mu all multiplied by a vector A. So this is the second property here. So it's closed under addition, closed under scalar multiplication. And there is the third one, there exists a null operator. So there exists a null operator. We will give it O, a null vector, or a null vector. Let's call it a null vector. Null vector. So the null vector is O. And this null vector, we can write it as, if we add the null vector means a vector with 0 components. If we add it to any vector A, it will give us the same vector A for all A's inside the vector space. Again, here, number 4 will give me multiplication by unity. We'll leave the vector unchanged. Unity will leave vector unchanged. So if we have 1 and we multiply it by a vector A, this should give me the same vector A. And 5, all vectors will have a negative vector such that, so we will define this as negative, existence of negative vectors, such that when we have the vector A, we add it to its negative vector negative A, this will give me what? Null vector. The null vector. And negative vector A is just negative 1 multiplied by the vector A. So if you want to check whether you have a vector space or not, all what you will do is you will come to the set of objects that you have. Let's say those objects are now vectors. And you will try to do this. You will come to the vectors of the vector space, try to add 2 vectors and see if the commutative addition holds or not. Try to do the associative addition holds or not. Try to see if the set is closed under the scalar multiplication. Try to see if you have a 0 or null vector or not, you have a negative vector or not, and so on. So you have to go through all the steps to check whether you have a vector space or not. So if we talk about, let's say, and this is what we will see maybe by the end of this lecture or next lecture for the examples, if we are talking about matrices, 3 by 3 matrix or 2 by 2 matrix, and you have matrices something like A, B, C, D, 2 by 2 matrix, for example, and you want to see if the set of 2 by 2 matrices will form a vector space or not. So what you will do is you will come to the first matrix A, B, C, D, second matrix E, F, G, H, and now you will do the addition, and of course the addition will hold. So the first matrix A, B, C, D plus E, F, G, H will be the same like E, F, G, H plus A, B, C, D, and this will hold. This will hold also. Okay, so you will do all of this, and you will notice that all the operation will hold for the 2 by 2 matrices. So it is indeed a vector space. That the matrices, 2 by 2 matrices, form a vector space. Then we will check other stuff like what's the dimension and what's the basis vector and so on. This is what we will be discussing in a minute here. So now we just define what do we mean by a vector space. So if you have a set of objects and you have those operation holds, this is what we define by a vector space. So let's move on and define the span of the vector space. What do we mean by the span of the vector space? So if we have a vector space A composed of vectors, now the objects are vectors A, B, let's say C, S vectors. So we have A to S vectors in the set. The span is defined as the linear sum of the original set. So let's say that we define a vector x, which is a linear summation of those vectors. So we have alpha, which is a scalar quantity, multiplied by A plus beta multiplied by B plus gamma multiplied by C plus and so on up to sigma multiplied by S. So this results will form an infinite number of possible values. There is infinite number of possible values of the scalar quantities. There is infinite number of possible values of alpha, beta, gamma, and so on up to sigma. So if we just have a vector space of A, B, C, D up to S, and we can form a vector here that's the combination of alpha A plus beta B plus gamma C up to sigma S. For all the possible values for alpha, beta, gamma, and sigma, we will have infinite number of possible values for those alpha, beta, gamma up to sigma. So if we have the summation this summation alpha multiplied by the vector A plus beta multiplied by the vector B plus gamma and so on multiplied by the vector C up to sigma multiplied by the vector S is equal to 0 for all alpha, beta, gamma, and sigma, not all zeros. So all of those constants are not 0. Maybe a couple of them are zeros, but all of them are not 0. Because if all of them are zeros, this is the trivial solution. 0 by A plus 0 by B plus 0 by C plus 0 by blah 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 plus 0 multiplied by S is equal to 0. This is the trivial solution. But if we can form a vector that is alpha multiplied by A plus beta multiplied by B up to sigma multiplied by S, and all those constants or the scalar multiplications are not 0, so in this case this is called linearly dependent vector. Why they are linearly dependent? Because you can keep this one in this side and move all the rest of the vector here to the right side, and this will be just a linear dependence of all the rest of the vectors. Yes, you can pick up any one, keep it in the left hand side, move everything to the right hand side, so you represent any of those vectors as the linear combinations of the rest of the vectors. So this is called a linear dependent. So this is called the linear dependence. So the set of all vectors x. So we will have multiple of x. It depends on the value of alpha, beta, gamma up to sigma. So let's say 1, 3, 5, blah 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 up to maybe 1,000. So this will be the first vector. then it changed the alpha, beta, gamma, and so on, second vector. Change the alpha, beta, gamma, third vector, and so on. So the set of all those vector x is said to be linearly dependent if this condition holds. So the set of all vector x is said to be linearly dependent. Linearly dependent. So the set of all vectors x that can be written as this form is called the span of the vector space. So the span of the vector space is all the set of vectors that you can write in the form of alpha A, beta B, gamma C, up to sigma S. Let's say that you have alpha, beta, gamma, up to sigma. You have certain numbers here. Here we have infinite. Let's say infinite possibilities. But let's say if you have a finite possibilities, if you have 10, let's say 10 of those vectors, the span will be 10. If you have 15, it will be 15. If 100, it will be 100. If infinite, it will be infinite. So the span will be just. The span is just the set of all vectors. Is the set of all vectors x. So let's move and define the linear independence. So the linear independence will be exactly the same like this one, but this will be not equal to 0. So if we have alpha multiplied by a vector A plus beta multiplied by a vector B plus gamma multiplied by a vector C up to sigma multiplied by a vector S, and this does not equal to 0, so I cannot represent any of those vectors as a linear combination of the rest because this is not equal to 0. Yes, it's equal to something. So you cannot just say A is equal to a linear combination of the rest. So if this condition holds, so in this case I will say that there is no any linear combination between one of the vector and the rest of the vectors. So this is just the definition. So the definition is no vector in the set can be expressed as a linear sum of the others. So if we have this definition, I cannot just grab one of those vectors and say this vector is equal to, and I move all the rest of the vector to the right hand side, and I said this vector is a linear combination of the rest of the vectors. So if this condition holds, there is no vector in the linear vector space that's formed from the rest of the vectors. Do you have any questions? I know that it's a little bit abstract, but you have to imagine it in your mind. So now we have to define the dimension for the vector space. So if in a given vector space, in a given vector space, there exists a set of n linearly independent vectors. But not set of n plus 1 linearly independent vectors, then the vector space is said to be n-dimensional. What does it mean? Let's come back to our vectors A, B, C, D, up to whatever, let's say Z or something like this. If we find in our set of vectors a set of vectors X equal to alpha A, beta B, up to sigma S. Let's assume that I look at my vectors A, B, C, D, up to Z, and I was able to form, let's say, 6 of those vectors. Only I found 6 that the summation of alpha A plus beta B plus gamma C is not equal to 0. Only 6. Okay? So in this case, the dimension of the vector space will be equal to 6. So the number of linearly independent vectors I can form in my vector space is the dimension of this vector space. But let's assume that I found a set of n linearly independent vectors, but there is no n plus 1, there is no 7. There is no 8, there is no 10. So the minimum number of sets, or the maximum number of linearly independent sets is the dimension of the vector space. So let's assume I formed here, let's say I assume that I formed here 3 sets of linearly independent vector space. The dimension is 3. I only was able to form 10. The dimension is 10, and so on. So let's assume that we are talking about the 3-dimensional vector space. So how many, what's the dimensional? I just stated, 3. Why? Because you will find 3 independent vectors, which is I, J, K. There is no, those are also called the basis of the vector space. So I, J, K. In 2 dimension you have what? I and J, or J and K, or I and K. So those are in 2-dimensional vector space. In 1 dimension you have only 1, which is I or J or K. Okay? So this is the dimension, the definition of the dimension for the vector space. So maybe we'll give some more definitions here before we go on and give some examples. So let's look at the real n-dimensional vector space. And sometimes we call it real and n, Rn. And it is defined as a set of all vectors with real component. So if all the vectors have real components, so in this case we will say that this is a set of all the vectors with real components will form the vector space. And of course, all the required conditions should be met, like the commutative and distributive property, or associative property, and also the scalar multiplication, the existence of the null vector, and the existence of the negative vector, and so on. So you have to verify that all of those exist. And also, we can define it as the set of all set of n linearly independent vectors with real components. So we'll define the basis vectors. So if we have V is an n-dimensional vector space, and again, V is a set of objects or vectors that satisfy the conditions that we just wrote, then if any set of n linearly independent vectors like E1, E2, E3, up to En. So those are a set of n linearly independent vectors do exist in this Vn dimensional vector space. They will form what we call the basis. Form basis for vector space V, like I, J, K for the three-dimensional vector space. Those are the basis vector for the three-dimensional vector space. Every vector in Cartesian coordinates can be represented as a linear combination of a I, J, K. So let's assume that we have a vector V with, let's say, 10 meters and has certain direction. So you can decompose the 10-meter vector into the three components: AX in the direction of I plus B, AY in the direction of J plus AZ in the direction of K. So if we have a vector space with n dimension, any set of linearly independent vectors can form the basis. And in this case, if we have X, a vector in this V in V is an arbitrary vector, so it can be represented by X equal to the components in the direction of those vector spaces. So it would be x1 in the direction of E1, x2 in the direction of E2, plus x3 in the direction of E3, and so on up to xn in the direction of En. You can in principle write any vector as this form here. So where xi are the components of the vector x, where xi is x1, x2, x3 up to xn. So xi are the components of vector x. With respect to, of course, ei. So maybe we can choose different basis vectors. If we choose different basis vectors, because maybe you can find, instead of just a set of linearly independent vectors, maybe you can find two sets of linearly independent vectors. So you will have two sets of basis vectors. You can attribute your vector to the first basis or to the second basis in this case. So in this case I can write the vector x still, but as x1 prime, because it has a component in the E1 prime now, plus x2 prime in the direction of E2 prime, and so on up to xn prime in the direction of En prime here. So now let's just give some examples. So the set of all 2 by 2 matrices, real matrices, in the form of A, B, C, D, where A and B, C, D are real numbers, will form real vector space. How will check this? By going back and checking this against the axioms that we just stated. So let's do, for example, some of those. So we knew that A plus B is equal to B plus A for the vectors. So let's check here. A, B, C, D plus E, F, G, H, and this is equal to same E, F, G, H plus A, B, C, D. Why? Because when you add matrices, you add the first elements in the row here to the first element, so it will be A plus A, and A plus A is just A plus A, and then you can decompose them again to the two matrices A and A here. And again, C plus G is G plus C, and D plus H is H plus D, and so on. So the commutative addition holds. Also, if we look at a scalar multiplication, the scalar multiplication we will notice that if we have C plus K multiplied by a vector here, or lambda plus mu instead, let's have the same consistent. Lambda plus mu multiplied by A will be equal to lambda A plus mu A, and so on. Just if you multiply lambda plus A multiplied by A, B, C, D, so you'll multiply the constant by everything, all the elements, so you will have lambda plus mu multiplied by A, lambda plus mu multiplied by B, lambda plus mu multiplied by C, lambda plus mu multiplied by D. Then lambda plus mu multiplied by A is lambda A plus mu A. So then you can decompose those. So again, so lambda A plus mu A matrices. So again, this will hold. So let's now look for the dimension. So if you just fulfill all the axioms that we just stated at the very early beginning of the class, you will notice that all the axioms will hold. So let's look at the dimension now for this 2 by 2 vector space, 2 by 2 matrices of vector space. So what do you think the dimension will be? Again, the dimension, we said that if we can form in this 2 by 2 real matrices, if we can form the maximum number of linearly independent vectors that we can form inside this vector space, this is the dimension for the vector space. And we will notice that the dimension for the vector space here is equal to 4. And usually why we'll find it 4? Because any vector can be represented as C1 multiplied by A0, 0, 0, plus C2 multiplied by 0A, 0, 0, plus C3 multiplied by 0, 0, A0, plus C4 multiplied by 0, 0, 0, A. Yes? So those are the 4 basis vector of the vector space. Anything, get any real number. So let's assume that this is the real number here, A is 1 or whatever, let's say 1. Then you can do any matrix inside the vector space by just multiplying C1, C2, C3, C4. Yes? So if A is 1, and let's say this is 2, let's assume that we want to build 1, 3, 5, and 9. So C1 will be what? Let's assume that A is equal to 1. So C1 will be what? 1 by 1 is 1. And C2 is what? 3. C3? 5. C4 is 9. Yes? So you can form any matrix by just doing the 4 bases of the inner dimension, the 4-dimensional vector space here. So did you understand this example? So in order to check whether it is a vector space or not, all what you would do is just look at look at the axiom, excuse me, check if the axioms, all of the axioms hold, and then once all the axioms hold, you will look for the set of n linearly independent vectors, for example, inside the vector space, and this will be the dimension, and those set of vectors will form the basis. So the set of vectors here are just 4, because I can form, those are linearly independent. This is linearly independent from those. Yes? Because if you add those 4, the addition will equal to 0 or not equal to 0. Not equal to 0. Yes? Except for C1, C2, C3, C4 all equal to 0. And this is the trivial solution. Yes? But for any scalar quantity C1, C2, C3, C4, I will not find values other than 0 to make this equal to 0. Yes? So, and the bases are those vectors. Do you understand? So maybe you can stop here and meet next time. Okay? Thank you so much.